Okay, so welcome back. Today we will continue to do from chapter 1 of Lang's book. Last time I must have mentioned this word Dedekind Domain, and we will introduce that today, and we will prove one of the important theorems from chapter 1 of Lang. So this will be, we will see in the slides it will come. So let me start sharing the screen and let's continue. Let's recall what we did in last 1 or 2 classes, and then we will continue from there. So please confirm that you can see the slides.
Yeah.
Okay. So as I said, this is the key word today, and Dedekind domains. I think I mentioned the word in one of the last classes. We will introduce that and continue. Okay. So in the last class and the last to last class, we have been looking at uh, how prime numbers, these properties about prime ideals in with respect to integrality, right? And we proved many things. We introduced the decomposition group and the inertia group. So these are subgroups of the Galois group associated to. So what is the picture? Small p is a prime. So you have a ring A and its quotient field K, a finite Galois extension L of K, and the integral closure of A in that is B. And capital P is a prime ideal of D lying above small p, and many of the results we proved under the assumption L over K is Galois, and this a ring, base ring A is integrally closed. These were the assumptions throughout. And then we introduced these groups, and we proved also that the decomposition field has two characterizations. One we proved last time, and one we proved in the class before that. It is the smallest for a certain property. This we proved in the class before that, before the last class. So what was this? Very quickly, what is the word here? What is the property for which it is smallest?
Exactly one prime ideal.
Yeah, exactly one prime lying above. And it is the largest for another property, which was, what was the keyword? This was in last class. The keyword here is splitting completely. Prime splitting completely we introduced. And for this last property, we proved we did not do it in general. We have assumed that the Galois group is abelian. So this was proved under an abelianness assumption. We proved the Galois group is abelian. Then this is the maximal field maximal subextension, such that a prime below splits completely. The decomposition field is with respect to that prime, and it is the maximal for which P splits completely in that field. And we showed that there's this canonical map. So what are the notations B bar and A bar here? A bar is A by P and B bar is B by capital P. And we showed that this residue field extension is normal, and let's assume it's separable, it's Galois. And you have a canonical map from the decomposition group at P, capital P, to this Galois group of the residue field extension. And we showed that this map is, what was the keyword? What was the most important result here? This map is, can one of you, surjective. It is onto, it is surjective, and we proved this. And then we assumed we are in number field situation. So these are finite extensions of the field of rational numbers, under which in that case A by P, B by P, etc. are finite fields. So this the Galois group here is a cyclic group of some order, and these are finite fields. And then there is a natural generator for this called the Frobenius, which is x going to x power q if your base field is fq. And the Frobenius, if you pull back, that is called the Frobenius automorphism here. So it'll be a class, because there is a kernel here which is called the inertia. So a Frobenius automorphism is any automorphism in the pre-image coset of the Frobenius map here. And if you assume that the inertia is trivial and also the group is abelian, then there is a unique thing, and that was what was called the Artin automorphism. And under the abelian situation, we showed that it does not depend on capital P; it depends only on small p lying down the prime ideal in the ground field. Okay, and that is called the Artin automorphism. So these are the things that we did last time, and if you want me to recall a bit more at the end of the class, if there is time, we can do. And today we will introduce the so-called Dedekind domains, and we will prove a very important result. So keep in mind, we are going to study Dedekind domains a bit more, because in algebraic number theory, we will be looking at ring of integers of a number field. So what does this mean? So you have a number field by definition is a finite extension of rational numbers. In rational numbers, you have the usual integers z, and you can take the integral closure of z in this finite extension. That is a ring of integers of that number field. And the point is, these are Dedekind domains. So if you take any number field and if you consider the ring of integers, those are examples of Dedekind domains. And therefore, since we are basically interested in those rings, we will be looking at Dedekind domains a bit more closely. And we are going to prove a very, very important result today concerning Dedekind domains. And this is, I don't know why I put question mark. It's a full stop. This is theorem 2 in Lang. Okay. So do you recall? Yeah, question mark is for the next thing. Can you recall theorem 1? I must have, for fun mentioned that Lang's book, very few things he is calling a theorem. Most of the results are called proposition or lemma or whatever. So theorem 1, do you recall? Up to now we have done only one theorem. So I am blindly following Lang in statements and in notations in everything. What was theorem 1? Do you recall? After all, there are not many theorems, so let's recall.
Was it going down theorem?
No, going down was not even stated in Lang. I went to Atia McDonald for going down. You remember in one of the classes we spent a lot of time in proving one particular proposition. So that's not the theorem. Do you remember that proposition? And I had several slides and I went a bit slowly through that, saying that it is important and
About a PID and its
yeah,
rank.
correct. So
Same also.
this proposition that I have in mind is, it needed two conditions, that the ring is Noetherian and the ring is integrally closed. And I introduced these notions whenever it was required in the proof. If you remember, I did not state the proposition. We started proving it, and whenever we needed, we put these assumptions. And that proposition was finally, if you have A is Noetherian and integrally closed, and you have the quotient field K, and if you have a finite separable extension L of K, and if you take the integral closure of A in that, then that is finitely generated as an A module. This was the important result that we proved. And theorem 1 was an immediate corollary to that. You take A to be a PID. So in particular, it's Noetherian. It is also integrally closed, obviously, because PID is UFD. All UFDs are integrally closed. And therefore, this integral closure in a finite separable extension is finitely generated as an A module. But A is a PID. So you have structure theorem for finitely generated module over PIDs. And therefore, it will have a free part, free of some rank. And there will be a torsion part, but integral elements cannot be torsion. So torsion is 0. So it is a free module. This is theorem 1. Of rank equal to what? The degree of the field extension. That I asked you to check, that was obvious. Okay, So this was theorem 1, and now theorem 2. So today we are going to do theorem 2, and that's all that we are going to do today. It's a very nice theorem, a very important theorem, and perhaps I should say that perhaps the most important aspect of this course is a particular theorem, a particular finiteness theorem, which I hope we will prove. We should prove, but if I am doing a bit more of other things, I don't know. We should be able to prove. In fact, that's the main point of this course. There is what is called a class group associated to a number field. Class group, CLASS group. Group is usual group. And this important theorem which we should be doing towards the end of the course is called is the finiteness of the class group. So this is a group that I have not introduced. Just keep the word in mind. Class group. It's associated to a number field, to its ring of integers, and it is finite as the most important theorem of this course. But in order to introduce the class group, we will do this theorem too. So let's do that today. So recall that in lecture 5, we started by proving that the integral closure is a ring. And you remember this proof? We use this fact that integrality can be characterized in terms of a finitely generated module with a property xm is contained in M, then x is integral, where M is a finitely generated A module, then x is integral over A. And I must have mentioned that this particular proof, which is given in Lang, is due to, do you remember whose proof this is? Only very rarely I have mentioned the proof is due to whom. One was Artin's proof for some finiteness of certain index, which we recall last class also. And this proof is due to whom? And I must have mentioned that this attribution I got from Milne's notes. Dedekind. Yeah, so this is Dedekind. So Richard Dedekind, I told at that time also 1831 to 1916. As usual, all the mathematicians coming in our lectures are German. Is there any non-German mathematician who has come in our lectures? In Artin Vapels, Artin is German, Austrian maybe. So yeah, that region. And Vapels I think is an American. And other than that, I think all were Germans. So Dedekind is also German. So usually from Wikipedia, I copy paste, I copy only the years just to give you a feeling, that what we are doing is quote unquote modern compared to, many other things that you do. Because typically, in MSc mathematics, even in electives, we will be dealing with Cauchy and Weierstrass and people of mostly of that time. So there is intersection. Of course, Dedekind is also from that era, but once in a while you see people, much more modern. But usually
Krasner was not German, no? I just googled it.
Say that again.
Krasner was not German, no? I just googled it.
Who?
Krasner.
Krasner, yeah, correct. Krasner is not German, and I must have mentioned in my lectures at that time that he is French, but he is originally from Russia. No, is that what you see?
Yes.
But he is French, yeah. He lived in France. Krasner. Yeah, I forgot. So thanks, yeah. So these are the extra things which make the lectures interesting. Okay. So here I have put the dates. Usually I don't put the dates. Do you want to take a guess why? Why did I put the dates? I have a lot to cover today. So
Today is 11th February.
Yeah, today is 11th February and I noticed 12th February. In fact, I thought of cancelling today's lecture and taking an extra class tomorrow for this coincidence to, not a coincidence, I mean planned coincidence, so to say. But I thought maybe we should not do so much in order to get the dates matching. So tomorrow would be his 105th death anniversary. 105 is correct, no? 16, yeah, 105th death anniversary. Okay, so let's start. Maybe I'll skip one or two slides because what I want to cover, I would like to cover because it's a proper full stop. So something which is not very difficult, maybe I will skip in order to save time. I hope that's okay. So a ring, which always you remember in Lang, a ring means commutative ring with unity, and it's actually an integral domain, no zero devices, is called Dedekind. I must have verbally said this once. Do you want to quickly recall what is the definition? It has 3 points in it. 3 things. Want to take a guess? Not quite a guess. We must have
Integrally
made
closed.
integrally closed. Yes, that's my second bullet
Again,
point.
Noetherian.
Noetherian,
And
that's my first bullet point.
I think dimension equals 1.
Cruel dimension is equal to 1. That is my third bullet point. Very good. So it is Noetherian, integrally closed or integrally closed up. Please remind me at the end, typo. So I'm doing all this, just before the class is starting. I'm finishing it off in a hurry without even rereading it. So, yeah. So integrally closed typo, one typo of cruel dimension 1. So what is the meaning of cruel dimension 1? Every non-zero prime ideal is maximal. Okay, so all these properties put together gives you a very nice structure, and we will see. You also, when I put bullet points, if I end with a full stop, then I would prefer to put a comma. Otherwise, nothing, no punctuation at all. That's usually my style. So I'll make that change also. I'm just repeating this so that I will remember. Okay, it's not meant for you. I'm telling myself. Yeah. So recall the crucial finite generation statement that we proved earlier. We just recalled under Noetherian and integrally closed. You got the integral closure in a finite separable extension is finitely generated as an A module, and that is the statement. And from this theorem 1 followed because of structure theorem for modules over PIDs. Theorem 1 was about a PID. Okay, so Dedekind domain, these first two properties already played a crucial role there. That's what I wanted you to recall. Most important example, a ring of integers of a number field. So O subscript K is a number field, is by definition the integral closure of Z in K, and it is Noetherian. Why is it Noetherian? Because of that result that we just recalled. So that result applies. Uh, no, that result. No, sorry. That result is about Noetherian integrally closed rings. So I'm sorry. We want to show that this is Noetherian. Uh, Oh, no. That result we are going to apply. Yeah, it is the integral closure of Z and K. And Z is Noetherian, Z is integrally closed. So that result you can apply here. This is your A. Yeah, so I was right. This is your A. And you are taking the integral closure of that in this. So OK, by that result, OK will be finitely generated as a Z module. OK will be finitely generated as a Z module by that result which we just recalled. And in particular, as a Z algebra, as a ring over Z. And therefore it is Noetherian as a ring. Why? This is enough. Quickly, can you tell me why? If it is generated as a ring over Z by finitely many things, then it is Noetherian. What is the key word? Oh, I should not ask too many things because I don't know how much of commutative algebra you have done. So if you know, you tell, otherwise it's okay.
Because that is Noetherian. So,
That is Noetherian, and therefore this follows, and there's a theorem.
any finitely generated module over a Noetherian ring is Noetherian.
Yes, but we should show that it's a Noetherian ring. So
Oh
any
yeah, then Hilbert basis theorem.
Hilbert basis theorem. Very good. So you have done this, is it?
Yes, I've done.
You have done it. Okay, good. So why the answer is HBT? Okay, so one more pause here. Hilbert basis theorem. Uh, yeah, so I could have given the biographical detail of Hilbert, but okay, anyway, this is not part of our course. But anyway, Hilbert might come, and anyway, Hilbert is too famous. All of you know about Hilbert. And it is integrally closed. A ring of integers is integrally closed. So because if x and k, so what is there to show? By integrally closed, I mean in its quotient field, it is integrally closed. Okay, so it is integrally closed over Z is clear because by definition it is the integral closure of Z in K. But what I need to show is it's integrally closed. It's integrally closed in its quotient field. So if you take x in K, and if it satisfies a polynomial with coefficients in OK, you have to show that x is what do you need to show? You need to show that x belongs there. No, we want to show, so once again, we want to show that OK is integrally closed. Yeah. So if you take something from the quotient field, which is K, and it is integral over OK, so the coefficients are in OK, it satisfies a monic polynomial, then this particular ring is finitely generated as a Z module. Why is that? Because we have proved long back that if the AIs are integral over Z, which is true because OKs are anything in OK are integral over Z. So if the AIs are integral over Z, then this is finitely generated as a Z module. Okay, and therefore if you attach X also, that is also finitely generated as a Z module because X is generated using these things, an minus 1 etc. a naught, and each of an minus 1 etc. a naught can be generated using finitely many things. So this is finitely generated as a Z module, and therefore Z of X is finitely generated as a Z module because this is a submodule of a finitely generated Z module. This is a finitely generated Z module, therefore it's Noetherian, and this is a submodule, therefore it's finitely generated. Submodule of a Noetherian module is Noetherian. So Zx is finitely generated as a Z module. What does this say? If Zx is finitely generated as Z module, then that says that X is integral over Z. By our characterization, X is integral over Z, and if X is integral over Z, by definition X belongs to OK, because OK by definition is the integral closure of Z in K. So in order to show that X belongs to OK, you have to show that X is integral over Z, and that's what we have claimed. Okay, so that shows that this is integrally closed, and it is also Krull dimension 1. So you have to show that any non-zero prime ideal is maximal. So suppose you take a non-zero prime ideal P contained in OK, and it is a non-zero ideal. So take an X belonging there, and because anything here is integral over Z, it will satisfy a polynomial in Zx monic with coefficients Bi and Z. Okay, and from this you can conclude that B0, the constant term, belongs to P. Why is that? Because X satisfies this and X is in P, and this much has an X in it. Therefore, all this product and sum, everything belongs to P. And this the total equal to 0. So B0 equal to minus of this, and this belongs to P. B0 is also in Z. So B0 belongs to P intersection Z. In other words, and therefore B naught times, if you take an element in OK mod P, let us say A plus P where A belongs to OK, then B naught times A plus P by definition is B naught A plus P, but B naught A belongs to P because B naught belongs to P. And A is in the ring and B naught is in P, so B naught A belongs to P. So in other words, B naught kills OK by P. Anything in OK by P, if you take B naught times that is a zero element there in OK by P. So OK by P is Z torsion. Anything as a torsion element. B naught kills everything there. So OK by P is torsion, and therefore you conclude it is finite. Why is that? I'm saying that OK by P is torsion and therefore it's finite. This is again structure theorem for modules over PIDs, right? Where Z is your PID. So the whole thing is torsion. There's no free part. There is only torsion part. And so torsion part will look like what? It will be an elementary abelian subgroup, right? Z module meaning a finite abelian group. So the torsion part is finite. And what did you conclude therefore? OK by P is finite. P is a prime ideal, right? P is a prime ideal. Therefore, OK by P is an integral domain. And it is also finite. What do you know about a finite integral domain? What can you say about a finite integral domain?
It's a field, right?
It's a field, and therefore P is
Maximal.
maximal. That's what we wanted to show, no? Any non-zero prime ideal is maximal. So finite integral domain is a field and P is therefore maximal. Okay,
So one more thing we can do, right, which is easier, like
say that
P
again.
intersection Z. So we can do one more thing, right, like which is easier, I think. That if P intersection Z, it is non-zero, right? Because
Yeah.
0 is the only prime ideal lying over 0.
Yeah.
So P intersection is non-zero, so P intersection Z is maximal.
P intersection Z is non-zero, and therefore
That
P
means it is,
intersection Z is maximal because Z is Z has dimension 1, you know. Therefore,
yes. So P is maximal.
you could have concluded like that also because we have already shown that yes, very good, very good. Is this Manav?
Yes.
Yeah, very good, Manav. That's a very nice proof. We have shown earlier that P is maximal if and only if the prime lying above there is maximal and P lies about P intersection set. Yeah, therefore P is maximal. Excellent. There also we used integral domain and field, but not this particular strategy. Similar, but not this particular thing. Yeah, so that's very good. Okay. So, so you know that the ring of integers of a number field. So you know, I mean, as an exercise, so I haven't stated it. You try to do. So, what is the most elementary number field that you know? Of course, Q itself is a number field, but the next basic number field will be Q root D, where D is something, right? So, if D is not square free, if D is not a square free integer, minus or plus, Q root D is a quadratic extension of Q. So it's a most elementary kind of number field. As an exercise, you try to calculate its ring of integers. Okay, so I leave it for you to check. So you can check that the ring of integers of a number field needn't be, no full stop here, AUFD. A basic example that you must have done in your algebra courses, if you take Q root 5, the ring of integers is Z root minus 5. And you know that this is not a UFD, no? This must have been your
Yes.
basic example of a UFD, which is not a, no. This must have been, yeah, I mean, nothing. You must have seen that this is not a UFD. Can you give a one-line answer? Forget the details.
1 plus root minus 5 into 1 minus root minus 5
Yeah,
is
that is
6.
same
And
as
2
the,
into 3 is also 6.
correct, correct. So you need to check that these are all irreducibles, and you have given two different factorizations. So in a non-UFD, prime element and irreducible element are different. So these are uh, so that way also one can argue, or otherwise, you know, there's no uniqueness of factorization. You need to check these are irreducibles, etc. You must have done all this. As an aside, we are not interested in this right now, but you might also recall this particular thing. More or less, people do all these things same time. Do you recall? So this is also ring of integers in the quadratic extension Q root minus 19. This happens to be the ring of integers. Do you remember this example? What was this an example of? And this is just for fun. I don't need this.
It's not a Euclidean domain.
Yeah, but it is a PID you must have proved. So
Yeah, I don't remember exactly, but
okay,
something
but
like
you remembered the one part. It is not a Euclidean domain, but it is a PID. So you have the standard inclusions, right? ED implies PID implies UFD, and typically counter examples one asks. So PID, but not an ED. This is the most standard example in most books, and UFD, but not a PID. What will be your standard example? That may be much easier. UFD, but not a PID. You have so many examples. Just give me one. Okay, so take something, no polynomials, and so take zx or something, right? Is that correct?
yeah, right. Yeah, it's
Yeah, that's not a PID. You have 2 comma x kind of IDs, and on the other hand, it's a UFD. So that is, you can bring too many examples like that, but this is not so obvious, but this is standard. Okay, it's a PID, but not an ED. So let's come to the topic only. Now we are coming to the topic for today. Half an hour is already over. So next is theorem 2 of Lang. I'm going to state the theorem, and I would like to finish the proof. So maybe I might take a few minutes extra, okay, if necessary, or I might go a bit faster. So next is theorem 2 of Lang. This is for a, so remember the theorem. This is a statement which is very easy to remember actually. Only thing that you need to remember is the theorem is for a Dedekind domain, and that was the title of my lecture. And we talked about Dedekind enough, so you will remember that. So just remember that theorem to happen today. when we discuss Dedekind a lot. So it's for a Dedekind domain. It has two parts. Okay. So let O be a Dedekind domain and let the quotient field be K. And first part says that unique factorization is true at the level of ideals. So here that was the point of this example. Ring of integers are Dedekind domains, but in Dedekind domains unique factorization need not be true. Dedekind domains need not be UFDs like this basic example shows. But what is true is at the level of ideals it is true. What is the meaning of that? Any ideal can be factored as a product of prime ideals. Okay, in particular, if it's a PID, then UFD is true. But but I mean PID is anyway UFD, so then it coincides. But otherwise, prime ideals can be factorized as product of primes in a unique way, but these are not UFDs. Okay, so there is something which one should mention here because but I will not. I ask you to, Google and read a little bit of history if you are interested. This famous Fermat's last theorem, all of you know about it, and it has a rich history. And there were these nice ideas which are unfortunately wrong in order to prove those. And one name you can Google in order to get the correct references, you can Google Kummer, a name that we have seen sometime, Kummer, Kummer. And there were these ideas. So if you assume that, your ring is a UFD, then there are nice ways of attacking that problem. That's how, ideal theory developed. All this algebraic number theory, a lot of algebraic number theory developed in attacking this one particular problem, Fermat's last theorem. Okay. Anyway, this history is well known. If you're interested, you read about it. We don't have so much time to spend there, or much later I might come back to it. Okay. But just remember that this is, these things came very nicely, historically speaking. So first part says unique factorization is true at the level of ideals. That is, any ideal is a product of, any non-zero ideal is a product of prime ideals in a unique way, meaning up to permutation. Second part involves the notion of a fractional ideal. Some of you might not have seen this term, so let me say what it is. It's an easy concept. So a fractional ideal for O or of O, it's not contained in O. So anyway, a fractional ideal for O or an O fractional ideal, it is an O module. Okay, let's call it A. It's an O module, but it's contained in K. It's not some random O module, it's an O module contained in K with a property that there is a non-zero number in O, number meaning an element in O, such that C times A is contained in O. Okay, so it is a module which is contained in the quotient field such that you can pick an element in your ring such that when you hit it with that, then that's contained in your ring. Okay, that's called a fractional ideal. So a basic example to keep in mind is something like half Z. You take all the rational numbers with 2 in the denominator. Okay, half integers, half Z, the set half Z, n by 2 where n is an integer. So what will you multiply with? What will be the most natural C which will do the job? You take 2. So 2 times half Z is contained in Z, half Z is contained in Q. So that's a fractional ideal. Okay. So second part involves the notion of a fractional ideal, and the second part says that non-zero fractional ideals of your ring, Dedekind domain, they form a group under multiplication. So if you take two fractional ideals, you can take the product. You have the notion of product of ideals. Similarly, you have the notion of product of fractional ideals. And because both are contained in K, you can take the product, right? So there's a notion of product of fractional ideals. And under this, it is actually a group. It satisfies properties of the group. So what will be the unit element? It will be the full ring O. If you multiply with O, nothing happens. And so what you need to show is every ideal is invertible. Every fractional ideal has an inverse fractional ideal. Given a fractional ideal A, there is a fractional ideal B such that A times B, the product of fractional ideals, is the unit element, which is O. So it's a very important theorem. It has two parts. One is unique factorization, and the second part is non-zero fractional ideals is actually a group. Okay, and this is where class group is coming. So this result says that non-zero fractional ideals will form a group, and then you can consider all the principal fractional ideals. What will be a principal fractional ideal? A fractional ideal which is generated by one element, like your principal ideals. Okay, and that will be a subgroup of this, and this you can take the quotient, and since we are in a commutative ring, this group is clearly abelian, right? A times B is same as B times A because our ring is commutative. So it's an abelian group. So taking quotient is fine, and every subgroup is normal, and you can take the quotient group, and this is what is called the class group, and this is finite. Is a big theorem of the subject, perhaps the most important theorem of this course. I hope we can do this. Okay, so non-zero fractional ideals for, so this theorem introduces for you what is called the class group of the number field. Okay, but we are doing this very generally for a Dedekind domain, and let's the proof in Lang is due to I often say Van der Waalen, but this is a Dutch name. So here is another mathematician, not from Germany, Netherlands, and this V is pronounced Fa. F, I think this V is pronounced like F, so it's Van der Waalen. But having said that, I might again say Van der Waalen because that's easier for me. Okay, so this is due to Van der Waalen, a Dutch mathematician, see quite modern, 1903 to 1996. So, yeah, so quite modern, yeah. So that is this particular proof. Of course, the result is much before this. This very beautiful proof is due to Van der Waalen. Okay, so we are doing Lang's proof, which is Van der Waalen's proof. The structure of the proof is as follows, and I would like to finish this proof today. The second part is proved first. We are going to show that the non-zero fractional ideals will form a group, and then we will show that every ideal can be written uniquely as a product of prime ideals. So we are going to show first that the second part, non-zero fractional ideals, indeed form a group in 4 steps. Okay, so I'll have slides called step 1, step 2, step 3, step 4, and you will see it's very nicely organized. And of course, if someone has given a good proof, beautiful proof, and if a famous textbook author has written it in a very textbook kind of way, then for me to look at it and copy paste it is very easy because it's beautifully explained in the book. What you really have to marvel at is how does one come with such a proof and how neatly it is packed. Okay, so that's always yeah, that's always a different thing. The ingenuity is in coming up with putting it like that. Anyway, we are just recalling the proof. So in 4 steps, and then the first part is deduced after this. So let's do step 1. So I'll have slides called step 1, step 2, step 3, step 4. All of you pay attention. It's easy because someone else has done it already. And we are going to use all the 3 properties that we have. What are the 3 properties? Noetherian, integrally closed, cruel dimension 1. All these will play a role. All these will play a role, yes, of course. So any non-zero ideal we want to factorize, right? So first claim is that any non-zero ideal contains a finite product of primes. This is our first claim, step 1. It contains a finite product of primes. Suppose not, then what can you say? There is at least one ideal which does not contain. What is a finite product of primes? P1, P2, etc. PR. Maybe repetitions are there. Okay, so if you assume to the contrary, there is at least one ideal which does not contain a finite product of primes, then you consider the collection of all such ideals which do not contain a finite product of primes. Okay, this collection is non-empty. Yeah, did you say something?
No, so now I think you can apply Swan's lemma.
Exactly. So
And then the maximal element should be prime, I think.
correct. So Noetherianness, and yeah, which is due to Zorn's lemma. You are right. So this collection is non-empty because of suppose not, and this has a maximal element because you are in a Noetherian ring, right? By Zorn's lemma. So why? Because of Noetherianness. So Noetherianness first time we are using, and this maximal element this maximal element, let's call it A, this cannot be a prime element, right? Why? This A is not a prime. Why? Because this is
It would
from which?
contain a finite product of prime, right?
Yeah, because one prime itself is a finite product of primes. Therefore, this is not a prime. Okay. Therefore, again by axiom of choice or Zorn's lemma or whatever, any ideal is contained in a maximal ideal. Any ideal is contained in a maximal ideal. So, oh no, sorry, I was jumping the gun. I am using the fact that it's not a prime ideal. I'll be using the other thing also very soon. So, because it's not a prime, there are elements x and y in O such that the product is in O, but neither x nor y is in, no, the product is in P, product is in A is your ideal, which is not a prime. Product is in A, but x is not in A, y is not in A. Agree? Because it's not a prime. Now what you do is, take A1 to be this bigger ideal than A. So you add x to A plus the ideal generated by x. So that's an ideal. Similarly, you construct A2, which is A plus YO. So both A1 and A2 are bigger than A. And therefore, what can you say? Uh, this A was maximal for this property. Because A1 is bigger than A1 contains a product of prime ideals. You agree? By the maximality of A1 is strictly bigger than A. So A1 contains a product of primes, A2 contains a product of primes, finite product of primes. But what do you know about A1 times A2? A1 times A2, when you multiply, it is contained in A because XY belongs to A. Because of this, A1 times A2 is contained in A. And that's a contradiction, right? So A1, A2 is contained in A by maximality. Each of the AI, A1 contains a product of primes, A2 contains a product of primes. Therefore, A contains a product of primes. That's a contradiction to the fact that A belongs to this collection. So the contradiction is because of this, and therefore you have shown that any non-zero ideal contains a finite product of primes. Okay with this proof? Okay. So this is step one. Any non-zero ideal contains a finite product. What are we trying to show? We are trying to show that non-zero fractional ideals will form a group, and the only thing that you need to show is any non-zero fractional ideal is invertible. Given a non-zero fractional ideal, you have to give a fractional ideal so that the product is identity. Identity is the full ring. This is what we have to show. So what we have to show is invertibility of fractional ideals. First, we have to show fractional invertibility of ideals, and then the invertibility of fractional ideals will follow. Okay, so step two is I'm going to do this, but for a maximal ideal first. I have to show that every non-zero ideal is invertible. I'm going to show right now that every maximal ideal is invertible. Okay, step 3 I will come to any ideal. So every maximal ideal is invertible. So let P be a maximal ideal. We have to show that P is invertible. You want to guess an inverse? In fact, for any ideal, I could have asked you to guess an inverse. Your guess may be correct, may not be correct, but no harm in guessing, no? Okay, at least guess the notation for the inverse. Forget the
R colon P maybe.
So, I don't know this
Colon P.
notation. What does that mean?
Set of all elements such that x into sorry. Set of all elements such that
Yeah, I don't know that notation. That's why I'm asking.
No, it's not what I said. That is not right.
Because that is purely ring theory, whereas here we are dealing with this quotient field also. Okay, so take a guess. I mean, let's do it. I mean, once I say it, it looks obvious. Not obvious, but we will do it. So this should be the notation, you agree, right? Because after all, it's going to be the inverse of P. Okay, so let's fix this notation. This is a set of all x in K in your quotient field such that x times P is contained in x in K such that x times P is contained in O. Okay, x in K such that x times P is contained in O. So that will be This is a good set to consider because finally, you want the inverse to have the property that inverse times this is equal to O. Okay, so this is one of the first things that you should consider. Okay, and so take this, and we are going to show that this is the inverse. Okay, we will show that P inverse times P is equal to O. Many times I'll write only one way because everything is abelian. Okay, so P inverse P equal to O. We will show this. So clearly P inverse contains O, no? Containing O, what do you need to show? 1 belongs there, but 1 belongs there because 1 times P, not just 1, any element of O if you take, if X is in O, then X times P is in O. So this containment is obvious by the definition of P inverse. We are going to show that P inverse strictly contains O. Okay, this is the crucial step in step 2. Clearly P inverse contains O, and our claim is that this containment is strict. So what we are claiming is that P inverse is not equal to O. Agree? Agree in the sense, I mean, the statement is clear. That requires a proof. For now, assume this claim and let's finish off this proof. Claim I will prove in the next slide. Okay, assume that we have proved that P inverse is strictly bigger than O. So now if you consider P, do you agree P is contained in P inverse P? That is clear because P inverse contains 1, no? P inverse contains 1 because P inverse contains O, so P inverse contains 1, so P is contained in P inverse P is clear. P inverse, yeah, P inverse P, and P inverse P is contained in O is also clear. P inverse consists of X such that XP is contained in O, so P inverse P is contained in O. But what is the property of P? What was this step? What is P? What is P? P is
Maximal.
maximal. Therefore, what can you conclude?
P inverse P is either equal to P or equal to O.
So check that P inverse P is of course an ideal because it has, it is a module, and the product is contained in O, so a module inside O will be an ideal. So this is an ideal. So the options are either P inverse P is P or P inverse P is O. And what do we want to show? We want to show that P inverse P is O. So what do we need to rule out? We need to rule out P inverse P equal to P. So the proof is there in the slides, but let me just say it verbally so that if I can recall without looking at it, then maybe it's easier for you to recall later. And since I typed this only an hour back, I do remember. So we just have to rule out P inverse P equal to P. Okay, and this is a very beautiful argument, and this argument we are going to use again and again, maybe at least twice more, certainly once more. Suppose P inverse P equal to P. Suppose P inverse P equal to P. That means if you take any element X in P inverse, then XP is contained in P, right? XP is contained in P if you take any element X in P inverse. But if XP is contained in P, do you agree that P is finitely generated over O? Because it's Noetherian, everything is finitely generated. So you've got a finitely generated O module P with the property that XP is contained in P. Okay, so what does that mean about X? What does that say about X? You've got a finitely generated module M such that XM is contained in M. M is an O module. So what does that say about X? X is, right? In the very first time when we started integrality, we showed that X is integral over A is equivalent to they being a finitely generated A module contained in the quotient fields, contained in the field such that X times M is contained in M. So that is integrality. So if X belongs to P inverse, and if P inverse P is P, then X times P is contained in P. P is finitely generated. Therefore, X will be integral over O. But if X is integral over O, then what can you say? If X is integral over O, then what are the properties of O? It's Dedekind.
X belongs to O.
X belongs to O. So if P inverse P equal to P, then every X in P inverse belongs to O. But that's not true. Agree? There is at least one X in P inverse which is outside O. That is the claim that we are going to prove later. So assuming the claim, we have proved that P inverse P cannot be P. Therefore, P inverse P equal to O. And that's what our claim was. We have an inverse for P. And this is obviously a fractional ideal. You can check this is a fractional ideal. This has, if X belongs here and Y belongs here, then X plus Y belongs there. If X belongs there and R is from R, O, then R times X belongs there. So it's a module is clear. And therefore it's a fractional ideal because anything in P times X is contained in O. So anything in P will work as your C. So it's obviously a fractional ideal. So that's a proof. So by maximality, P inverse P equal to P or P inverse P equal to O. If P inverse P equal to P, then any X in P inverse leaves a finitely generated O module, which is P, invariant. Invariant meaning XP is contained in P and therefore is integral over O by the characterization of integrality. And O is integrally closed. So last time we used Noetherianness. Here also we are using Noetherian, by the way. P is finitely generated is because of Noetherian. And because of integrally closed, P inverse and P inverse is not O. That is the claim that we are assuming. Because of that, we get a contradiction, and because of that, we know that P inverse P is not P, and therefore P inverse P is O, and that's what we have to show. So what do we need to show for step 2? We have to prove this claim. What is the claim? P inverse is strictly bigger than O. That is the next slide. So P inverse a fractional ideal is obvious. Check it. So we need to prove now that P inverse strictly contains O. Only then step 2 is complete. So let's do that. So let X be in P inverse. No, let X be in P. And we want to show that P inverse is strictly bigger than O. Okay. So let X in P and choose R minimal. Okay. For the property such that P1 times etc. PR is contained in the ideal generated by X. Okay. So by step 1, you know that any ideal contains a finite product of primes. Right? That was step 1. Any ideal contains a finite product of primes. So if you choose any X in P and take the ideal generated by that, in particular, this ideal contains a finite product of primes. So it might contain in different ways, but choose R minimal for this property that contains P1 etc. PR, and this R is minimal. Okay, so you can do this. And of course, this ideal is contained in P because X belongs to P. Okay, where PIs are prime ideals because this contains a finite product of primes, and we are using this minimality, and we have chosen this minimally. PIs are prime ideals. But if a product of primes is contained in one ideal, what can you say? If a product of ideals is contained in a prime ideal, what can you say? If I times j
one of them is contained in that
one of them is contained in the prime ideal. So using the primality of this, not the primality of these things, but the primality of this, you can say that one of the PI is contained in P. Agree? One of the PI is contained in P. But then, because Krull dimension is 1, what can you say?
PI equal to P.
PI equal to P. Okay, so without loss of generality, I am taking I to be 1 because it's commutative. No, whatever is that PI, rearrange and put it to the first thing. So without loss of generality, P1 is contained in P, but then P1 equal to P because of Krull dimension.
You chose PI to be non-zero, right? That is.
PI is non-zero. So when we are saying here itself, our first claim is, see, sometimes non-zero I may not stress. Our first claim is every ideal contains a finite product of non-zero prime ideals. Okay, because if one ideal is 0, then of course there was nothing to prove, no? Because 0 times anything is 0, right? And
R minimal won't make any sense. It would just be 1.
Say that again.
Like if 0 ideals are admitted, R would just be 1.
Yeah, no. So what I'm saying is, so I did not stress it here, but here itself in my step 1, finite product of primes, I mean finite product of non-zero primes.
Yeah.
Okay, so maybe I will add that because it's better to be correct, but I meant non-zero primes. Yeah, our proof also showed that only, no, because otherwise there's nothing to show, right? Every ideal contains zero, so the it is product of non-zero primes. So among the non-zero primes, you have chosen R minimally. So Pi is a non-zero is given. Right? You know that this contains a product of non-zero primes. Among those ways of writing, you have chosen R minimally. So Pi is a non-zero. And yeah, sorry, I went ahead. So because of full dimension 1, P1 equal to P and P1 equal to P. So therefore, and also you know that P2 times etc. PR is not contained in X. Why is that?
Well, R is minimal.
Because R is minimal. These are only R minus 1 here. So because R is minimal, this is not contained in X. In other words, so this by minimality. Therefore, this is not contained in this means what? There is an element of this which is not in this, right? There is an element of this which is not in this. So there exists a Y in P2 etc. P2 times dot 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 PR, the product, which is outside X because of minimality. Okay, now let's argue with this. If you take y times p is p1. Okay, so y times p1, y times p is y times p1. What do you know? Y times p1 is contained in p1 times etc. p2 times etc. pr. So y times p is y times p1, which is contained in p1 times etc. pr, which is contained in x. That is given to us. So y times p is contained in x. Therefore, y times x inverse times p is contained in O, right? This is x times O. So if you multiply by x inverse on both sides, y x inverse p is contained in O. Y x inverse p is contained in O. But y x inverse is, yeah, so this implies y x inverse belongs to p inverse. Agree? That was the definition of P inverse, no? P inverse consisted of all those elements of K with the property that alpha times P is contained in O. So because of this, Yx inverse belongs to P inverse by the definition of P inverse. But Yx inverse is not in O because Y is not in X, ideal generated by X. So Yx inverse is not in O. So you have demonstrated an element of P inverse which is not in O. Yx inverse is not in O since Y does not belong to X. So you have demonstrated, you have exhibited an element in P inverse which is not in O. So P inverse strictly contains O. This is what we wanted here at this stage. Assume the claim. And therefore now step 2 is fully proved. So step 1 was every non-zero ideal contains a finite product of non-zero prime ideals. And step 2, we want to show that every ideal is invertible and every fractional ideal is invertible. And step 2, we have shown our claim for maximal ideals. Every maximal ideal is invertible. Okay, let's come to step 3. So you can see, right? I mean, from one line to the next line, everything is obvious. But I mean, I still marvel at, how does one think of all these things together? Maybe, from experience, whatever. Yeah. So very, very beautiful steps put together. Okay, so step 2 and step 3 is I am removing the word maximal from step 2. We have proved that every maximal ideal is invertible, and now I am saying that every non-zero ideal is invertible and inverse is a fractional ideal. So my claim is every, right, P inverse was a fractional ideal, no, earlier. So similarly, my claim here is every non-zero ideal is invertible by a fractional ideal. Given an ideal A, would you like to guess what the inverse will be finally? For the ideal P, we said that P inverse is the inverse, and P inverse I defined as set of all x in K such that x times P is contained in O. Do you want to take a guess? If the world is nice, let us say, what would be the inverse of A?
Same, right?
Same. Just change the notation P to A inverse, which is defined as set of all x in K such that x times A is contained in O, and That is of course a fractional ideal, and that should be the inverse. So what we have to show is that A times A inverse is O. But the proof is a bit roundabout. Proof is a bit roundabout. We will use step 2 and conclude this. Okay. Finally, that's what we are going to show. So your guess is absolutely right. So suppose not. Every non-zero ideal is invertible by a fractional ideal. Suppose not. Then there is an ideal which is not invertible by a fractional ideal. Take that collection and take a maximal element, earlier arguments, Zorn's lemma, Noetherian, etc. So choose one maximal amongst the non-invertible ones by fractional ideals. Okay, exactly like earlier. So once again, we have used the ring being Noetherian. Call this A. So A is maximal for what property? It is not invertible by a fractional ideal. Among such ideals, you have chosen a maximal ideal, maximal for that property, and that is A. So A is not invertible by a fractional ideal. Can A be a maximal ideal of O? This is maximal for this property. Can this be a maximal ideal of O?
No, because maximal ideals are invertible.
Yes, by step 2. By step 2, maximal ideals are invertible. Therefore, A is not maximal. Answer is no. Why? Answer is step 2. Therefore, it is contained in it's properly contained in a maximal ideal, right? This is also Zorn's lemma, no? Maximum of choice, whatever, Zorn's lemma. Every ideal is contained in a maximal ideal. This is where your ring theory starts. So A is strictly contained in a maximal ideal P, where P is a maximal ideal. You have the natural definition of A inverse. What is it? Set of all x in K says that x times A is contained in O, and it's easy to check that it's a fractional ideal for O. And clearly P inverse is contained in A inverse, no? A is contained in P, therefore P inverse is contained in A inverse, because if you take x in P inverse, then x times P is contained in O, but if you take something in A, x times A is contained in x times P, which is contained in O. So this is obvious. Clearly P inverse is contained in A inverse. And now let us check, take A. A is contained in A P inverse. Why is that? Because P inverse contains 1. All these inverses are big. They contain O. So they contain 1. So A is contained in A P inverse is true. And P inverse is contained in A inverse. So this is clearly contained in A inverse. And A inverse by definition is contained in O. So you have this thing. Okay. Now, the earlier argument that I first said verbally and then showed the slides, do you think you can apply that to this? Earlier I showed that P inverse times P is not equal to P. What was the argument? There we used integrally closed. Same argument can be applied here, no? I want to show that this is strict. If this is not strict, what will happen? P inverse A equal to A. But A is finitely generated, right? Every ideal is finitely generated. So you've got a finitely generated module contained in the quotient field such that P inverse x times A equal to A if x belongs to P inverse, which will show that x is integral over O, because A is an O module. A is an ideal, which means an O module. So x is integral over O, but O is integrally closed, therefore x belongs to O. X belongs to O. That means any element of P inverse belongs to O. But that's not true, right? P inverse is not O. Why P inverse is not O? Because in step 2, we have made the claim that if you have any maximal ideal, P inverse strictly contains O. P inverse is not O for any maximal ideal. P is what we have shown as part of step 2. So same proof applies. So P inverse strictly contains O and O is integrally closed. You will get a contradiction if this was an equality. So the claim is that this is strictly contained and this is a strict containment, exactly the same argument as in the proof of step 2. If P inverse A is A, then P inverse would leave a finitely generated O module invariant, making each element of it integral over O, and that cannot be the case because O is integrally closed and P inverse strictly contains O, which also we proved last time in step 2. This is true for any maximal ID. Was it too fast? Is it okay? This is an argument that we have done earlier, so I was a bit fast. Okay, so this is strict. Now you tell me the next thing. What will be the next claim? Because this is strict, because AP inverse is strictly bigger than A, what can you conclude about AP inverse? A had a maximality property. A was maximal.
AP inverse is equal to.
Yeah, A was maximal amongst the non-invertible ideals. Therefore, AP inverse is invertible by a fractional ideal because it is strictly bigger than A. So A is strictly contained in AP inverse and AP inverse is an ideal. It is contained in O. So by maximality of A for non-invertibility, we see that this is invertible, which means there is a fractional ideal B such that AP inverse times B is O. But then you are done. So A has an inverse. What is the inverse of A? A inverse of A has the inverse P inverse B. A times P inverse B is O. B is a fractional ideal, P inverse a fractional ideal, therefore this is a fractional ideal. So A times a fractional ideal, which is P inverse B together, so you have shown that A is invertible. But that's a contradiction. That's a contradiction to the fact that A belongs to the non-invertible sets. And that shows that this is not true. Therefore, every non-zero ideal is invertible by a fractional ideal. So step 3 is done. Let me do a bit more in step 3 beyond the claim. So because as Manav said, the inverse should be A inverse. I haven't shown that yet. Let us show that also as part of step 3. So every non-zero ideal is invertible, we have shown. Already we have shown because of this contradiction. Okay, so note that at this stage, we haven't yet proved that A times A inverse is O. A inverse is defined, but we haven't yet shown. What we know is A times A inverse is contained in O. But it's easy now. This is also true because what we know is there is a fractional ideal, let us say C, such that A times C is O, because that's what we claimed and that's what we proved. So A times C is O. Clearly C is contained in A inverse because A inverse consists of those elements X such that X times A is contained in O. So if X belongs to C, then X times A is contained in O. So C is contained in A inverse is obvious by the definition of A inverse. So we have to show the other way. I want to show that A inverse equal to C. A inverse is contained in C. So conversely, if X belongs to A inverse, then I have to show that X belongs to C, but that's easy. Because if X belongs to A inverse, then X times A is contained in O by the definition of A inverse. Therefore, X times A times C is contained in X times A is contained in O. So if you multiply by C, X times A times C is contained in O times C, but that is just C. So X times A times C is contained in C, but AC is O. So X times O is contained in C, in particular X belongs to C. So that's the other way. So A inverse is contained in C as well, and therefore this is also fine. So C is actually equal to A inverse. So what Manav said at the starting that the inverse should be A inverse is now fully proved, but we have proved it in a roundabout way. By reducing it to the maximal case, we said there exists an inverse, and having shown the existence of an inverse, we showed that that inverse has to be A inverse. So it's done in a roundabout way. Now step 4 is that every non-zero fractional ideal is invertible. Up to now, what have we done? We have shown that every ideal is invertible. Every non-zero ideal is invertible. Now this is easy, reducing it to fractional ideal, because if you take any fractional ideal non-zero, by definition there is an element in the ring of in the Dedekind domain O such that CA is contained in O. That's the definition of a fractional ideal. There is a non-zero C such that CA is contained in O. But by step 3, so CA will be an ideal, no? If A is a fractional ideal and if CA is contained in O, then CA is actually an ideal, an integral ideal, a proper ideal, a genuine ideal. And every non-zero ideal, and this is non-zero because A is non-zero. and every ideal is invertible by a fractional ideal. Therefore, by step 3. Therefore, the ideal CA is invertible by a fractional ideal by step 3. That is, there exists some fractional ideal B such that CA times B is identity, the full ring. But then A has an inverse. Now, what is the inverse of A now? From this, A has an inverse. What is the inverse of A?
CB.
CB. So A has an inverse, which is CB. I should put a pause here. And therefore, we have proved that non-zero fractional ideals of O form a group, right? Only invertibility you had to show. It's an abelian group. Commutativity is obvious. The unit element is O, and associativity, whatever other properties, all of them are obvious. Only invertibility you had to show, and you showed that any non-zero fractional ideal is invertible. What remains to be proved in theorem 2? What is remaining? So we have time, we can prove. I have 10 minutes, that's more than enough. What is the last thing to prove?
Every ideal is a product of prime ideal.
And in a unique way. Okay, so now the proof is something which you can yourself do, because though it's non-obvious, it's obvious because the argument we have used many times. So let us do factorization in this slide and uniqueness in the next slide. Uniqueness is completely obvious. Factorization let us do. So if there is an ideal which can be written as a finite product of, we want to claim that every ideal can be written as every non-zero ideal can be written as a finite product of prime ideals. Okay, this is what we have to show. Suppose not. So there is an ideal which cannot be written as a finite product of prime ideals. Why don't you finish the proof? What will you do? You take what collection? You take the collection of same argument as before. You take the collection of
Product of prime ideals. Oh yeah,
ideals.
take the collection and take it maximum element.
Yeah, exactly. So take the collection of ideals which cannot be written as a finite product of non-zero prime ideals, and by Noetherianness choose a maximal one and argue with that. So let's see. So choose one maximal for this property because of Noetherianness, call it A. So A cannot be written as a finite product of prime ideals, and A is maximal for this property. Okay, and as earlier, A is not a maximal ideal, right? Because the maximal ideal is a prime ideal. If A itself is a prime ideal, then of course it's a finite product of prime ideals. So therefore A is not a maximal ideal, and therefore strictly contained in a maximal ideal P. Exactly like earlier. This is strictly contained in a maximal ideal P. And we have time, so I'm getting a doubt about one of the earlier arguments. Let us just go back. And somewhere I use the same argument of full dimension 1. Here P1 is, okay. So I said that PIs are prime ideals. Therefore, one of the PI is contained in P. That is using the fact that P is a prime ideal. And without loss of generality, P1 is contained in P, and therefore P1 equal to P because every non-zero prime is maximal. Correct. Yeah, this is fine. Yeah. Now I was thinking, why didn't I argue with maximality but with primality? But that was my claim. Can be written as a product of primes. This is fine. Perfect. So coming back, we have chosen something maximal for this property, and maximal for this property. Therefore, this A is strictly contained in. This is not maximal. Therefore, this is strictly contained in a maximal ideal P. And because A is strictly contained in P, A times P inverse. P inverse and all we have already defined in the first part. So A times P inverse is strictly contained in O. Why is this? Why is this true? Because if A times P inverse is equal to O, you can multiply by P on both sides and you will get A equal to P. But that's not true. So AP inverse is strictly contained in O, and AP inverse contains A. A is strictly contained in AP inverse. What is the argument for this? So this is the third time the same argument is coming. If A equal to AP inverse, we get contradiction to what? We get contradiction to O being integrally closed, because P inverse will leave a finitely generated O module invariant, and P inverse is strictly bigger than O, and O is integrally closed. All these put together, we get a contradiction if it was an equality. So this is strict containment. As earlier, A is finitely generated, P inverse is strictly bigger than O, and O is integrally closed. And therefore, what is your conclusion? AP inverse is an ideal, is a proper ideal, which is strictly bigger than A, and A is maximal for some property. Therefore, AP inverse, what can you say? This can be written as a product of non-zero prime ideals. So therefore, it has a factorization by maximality of A. But if AP inverse has a factorization, then of course A has a factorization, no? If AP inverse is P1 etc. PR, then A is P1 etc. PR times P. So A also has a factorization. Okay, this proves factorization. So only thing remaining is uniqueness. So suppose an ideal is written as a product of primes. There may be repetitions. P1 may be equal to P2. I don't care. So if P1 etc. PR, the product is equal to Q1 etc. QS as a product, how will you finish off uniqueness? You take one of this. You take P1. P1 divides this product, right? What is the meaning of an ideal dividing? What is the meaning of P divides A? What is the meaning of ideal P dividing ideal A? Yeah, this is standard notation, no? What is the meaning? Right, 2 divides 6 as natural numbers. So what does that mean in terms of ideals? 2z and 6z. What is the containment?
Saying that there exists some J such that I into J is equal to
No,
J.
no, no. In general, I am not talking about Dedekind domains. In your ring theory, there is a notion of I dividing J, right? You
Does
cannot
that
say you cannot say that J is a product of something. No, I mean in general.
you can write product of ideals?
In general, you have product of ideals. So is what? Okay, fine, fine, fine. So in terms of containment, what you said can be rephrased as. You're right. You're absolutely right. But in terms of containment, what is contained in what?
I into some K is contained inside J.
Correct. So you get that containment. So yeah. Therefore, in particular, so if P divides A, then A is contained in P, right? If P divides A, you are saying A equal to P times something, and P times something is contained in P. Therefore, A is contained in P. Your usual notion, whatever, yeah. So P1 divides this, therefore P1 divides this. But if P1 divides this and P1 is a prime ideal, therefore what can you say? So P1 divides this means this product is contained in P1. But P1 is a prime ideal. Therefore, what can you say? One of them is contained in P1. P1 divides one of this, or one of them is contained in P1. So then P1 divides Qi, that is Qi is contained in P1 for some I. By maximality, P1 equal to Qi, right? P1 is Qi is contained in P1 and all these are maximal. Every prime is maximal. So Qi is maximal. Therefore, P1 equal to Qi. But if P1 equal to Qi, you multiply by P1 inverse on both sides. What will you get? You will get P2 times etc. PR equal to, here Qi you remove the remaining. Therefore, you are done by induction. You have brought to length one less. So you have done by induction. Therefore, the conclusion is R equal to S and the factors are equal up to a permutation. Okay, so that shows uniqueness. So yeah, so we are done within time. So there are a few typos which I will correct. Let's not discuss it now. There's so much, not so much time. By the way, my general request. So whatever typos I remember, I correct it. Not just typos. Sometimes they may be slightly non-trivial mathematics also. For example, last time in one of the things, I wrote B, and then it was not quite clear in the class, and then I said we will argue with A bracket alpha. This was one of those corollaries to the surjectivity result. And that then I kind of convinced myself in the class that maybe that was good enough, but that was not quite good enough. But that idea was correct, and that I had filled up. I referred to some place and I actually filled it up. So such things I am changing when I put in Moodle. And what I wanted to say is, even in Moodle, if you see any typo, please let me know. Send me an email or a WhatsApp message, because I would like my slides to have no typos, including, spelling mistakes and punctuation marks. If you see anything, don't think that, oh, it's anyway trivial, so no need to tell him. Please don't think like that. Whatever you see, which is not quite correct according to you, let me know by email or by WhatsApp. So that I will double check, and if I am happy with what I have written, I will leave it as it is. If I think you have a point, I will correct it. Okay, so please do so. So here also there are many typos which I will correct, including, I should have written non-zero prime ideals, etc. I will make those changes and put on Moodle. So let's stop the class here and stop sharing the screen. Okay, it's almost time. Anyway, let me stop recording also. Anand, you want to ask something? Let me just stop recording and you can ask.